In the present video, current electricity part 1, we will be studying about the following. What is electric current? Different types of electric current, SI units of electric current, and we will also study why current can be taken as a scalar quantity. By definition, electric current is defined as the rate of flow of charge with time through any section of a conductor. Mathematically, current I is total charge divided by total time equal to Q by T. The expression is used to get the average value of current in a circuit because it's ratio of the total charge to the total time. It also gives us the current, rate of flow of charge or current, if it is steady, that is if it doesn't vary with time. For varying currents, we calculate instantaneous value of current because it's going to change next moment. The value changes with time, so we write I instantaneous equal to dq by dt. This is when the current is varying or it changes with time. The types of current, here is a graph which shows variation of current with time. The current which does not vary with time is called a steady current. Curve 1, here this curve 1 represents steady current. As you can see, the graph is parallel to the time axis. The current which varies with time is called varying current, except for one. All graphs represent varying current. 2, 3, 4, these represent varying currents because their value continuously changes with time. Then we have another way of classification of currents, the direct current and alternating current. If a current continuously flows in same direction, then we call it direct current. The graphs 1, 2, 3 and 5, 1, 2, 3 and 5, they represent direct currents because they have only positive values. The direction doesn't vary with time. However, if the current varies both in magnitude as well as direction, we call it alternating current. The curve 4 represents alternating current. Now let's define SI unit of electric current. Electric current is a scalar quantity with SI unit ampere. Capital A is the symbol for ampere. The current in a conductor is said to be 1 ampere if a charge of 1 coulomb crosses any of its cross section in 1 second. That 1 coulomb charge means 6.25 into 10 to the power 18 electrons per second. The smaller units of current are, we use prefixes with ampere as usual. 1 milliampere 10 to the power minus 3 ampere. 1 microampere as 10 to the power minus 6 ampere. Conventional direction of current. Remember, current is a scalar quantity. Why we take it as a scalar, we'll discuss. But then we assign a conventional direction to it. The direction of motion of positive charge is taken as the direction of flow of current. So the current flows from higher potential to the lower potential. If V1 is at a higher potential than V2, the positive charge will flow from V1 to V2, and this also will be taken as direction of current. Electrons move towards higher potential, so electrons drift in a direction opposite to that of current. This is positive, the electrons are moving towards right and the current is flowing towards left. So again the same things restated. This implies that the drift of electrons is against the direction of current. If V1 is greater than V2, the current flows along CD, that is from higher potential to the lower potential. Now, why is current taken to be a scalar quantity? For this, let's consider these three figures. In the first one, figure A, we have two forces acting on a block. Remember, if both the forces act in same direction, here they are acting at an angle. If they act in same direction, the net result will be sum of the two, F1 plus F2. If F2 is applied from opposite direction, then the net effect will be their difference. If they are perpendicular to each other, the net force will be different, you know from your knowledge of vector addition. However, in figure B, we have a wire. Here it is straight and here it is bent. This wire is a part of electric circuit, say a table lamp being lit. If the wire is straight or if it is bent in the way shown here, there is no effect on the light received from the table lamp. So current is a scalar quantity. Similarly, another factor in favor of this current taken as scalar is it is algebraic sum. We have to take the algebraic sum here at this point, at this junction. We are getting two currents, 2 ampere and 4 ampere. The total current is 6 ampere. Even if you change this angle, the current will add up to 6 ampere. This is how it differs from the vector addition. Here, if the angle is changed, the net force will be different. Here, if the angle between conductors is changed, there is no change in the total current. This is restated. For a vector, say a force, the effect changes with a change in direction. However, for current, the bending of a wire doesn't alter the effect on the lamp. Unlike vectors, the current follows laws of scalar addition. You may subscribe to our channel CBSE 042 and like the video. For any feedback, write to the mail ID ikg54@yahoo.co.in, and you may visit this blog physicsbeckons.wordpress.com for more topics and videos. Happy learning. Thanks for watching.